Every time you drive an electric car, a computer makes thousands of decisions every second to protect the most expensive component in the vehicle. Without it, your battery could lose capacity much faster, charge unsafely, or even fail prematurely. That invisible computer is called the Battery Management System, or BMS, and today we are going inside it. Inside a modern traction battery, hundreds or even thousands of individual lithium-ion cells are packed tightly together. Wiring these cells directly to an electric motor without intelligent control would destroy the entire pack. Left unsupervised, individual cells charge at different speeds, develop dangerous localized hotspots, and degrade unevenly, causing premature battery failure. The battery management system prevents this by operating as the pack's brain and nervous system. This hidden computer continuously measures cell voltages, monitors temperature distributions, and regulates current flow. It manages everything from thermal control and cell balancing to estimating state of charge. Through constant active supervision, the system coordinates thousands of separate chemical cells, forcing them to function as a single, stable, and safe power supply. This level of control relies on high-precision, real-time measurement. Dedicated monitoring chips trace the voltage of every individual cell down to a fraction of a millivolt, hundreds of times every second. Simultaneously, the system tracks overall pack voltage, bidirectional current flow, and localized temperatures using a network of sensors. From these raw physical metrics, the computer calculates two standard indicators: state of charge, which acts as the battery's fuel gauge, and state of health, which measures the pack's physical condition and degradation over time. This micro-level tracking is necessary because a single weak cell limits the performance of the entire battery pack. If one student in a classroom starts falling behind, the teacher notices before the entire class is affected. By identifying minor voltage drops or subtle thermal changes instantly, the onboard computer acts to prevent damage and optimize energy delivery long before the driver ever notices a problem. To protect the battery from permanent physical damage, the system enforces a strict, safe operating window. Lithium-ion cells must stay within precise voltage limits, typically between 3.0 volts and 4.2 volts. Pushing a cell above its upper limit degrades the liquid electrolyte, generates heat, and accelerates aging, creating a severe safety risk. At the other end of the window, letting a cell discharge too far triggers a destructive chemical process called copper dissolution, where copper dissolves into the electrolyte, forming conductive metallic structures that can permanently short-circuit the cell from within. This is why the onboard computer continuously regulates the flow of electricity during both alternating current and direct current charging. During direct current fast charging, the system dynamically scales back the charging power in kilowatts as the battery fills, rather than holding it at a flat maximum. And when the dashboard displays 0%, the pack is not actually empty. The management system maintains a hidden safety reserve, a buffer designed to prevent the cells from ever entering the hazardous deep discharge zone, preserving the overall lifespan of the pack. Even identical battery cells straight from the factory possess tiny physical variations. Over time, these manufacturing tolerances, combined with natural aging and uneven temperature exposure, cause individual cell voltages to drift apart. This is where cell balancing becomes vital. Imagine several water bottles connected together. If one bottle is always fuller or emptier than the others, eventually the entire system becomes inefficient. To resolve this, the battery management system, BMS, employs two main balancing techniques. Passive balancing uses simple shunt resistors to drain excess energy as heat from the most charged cells. Active balancing is more advanced, utilizing specialized bidirectional converters to transfer energy from high voltage cells to weaker ones with up to 92% efficiency. By redistributing this energy, the BMS brings all cells back to a uniform voltage, maximizing the usable capacity of the pack. Because this process requires stable conditions, the computer typically performs these micro adjustments while the vehicle is parked or actively charging. Like the chemical reactions they rely on, electric vehicle battery cells are highly temperature sensitive, operating best within a narrow window of 15 to 35 degrees Celsius. To maintain this ideal environment, the Battery Management System, BMS, coordinates complex liquid cooling loops, resistive heaters, and refrigerant heat pumps. Temperature directly dictates performance, aging, and safety, which explains the winter range loss we discussed in our previous episode. Before direct current fast charging, the BMS actively preconditions the pack, warming or cooling the cells to prep them for a high power input. This thermal regulation is especially necessary during cold weather charging. If high power charging is attempted below 10 degrees Celsius, the lithium ions cannot easily penetrate the anode. Instead, they deposit on the surface as metallic lithium, a highly destructive chemical reaction known as lithium plating that causes permanent capacity loss and internal short circuits. To prevent this damage, the BMS automatically limits charging power, delaying rapid charging until the cells reach a safe temperature. We'll explore lithium plating in much greater detail in a dedicated episode. Subscribe to stay updated on our latest engineering breakdowns. A gasoline car uses a simple float to measure fuel, but an electric vehicle battery cannot directly measure its remaining energy. Instead, the Battery Management System, BMS, must calculate it mathematically. The computer estimates state of charge, remaining range, and available power using Coulomb counting, tracking current flowing in and out of the pack, while applying voltage estimation and temperature compensation through advanced algorithms like Kalman filters. This intelligence is broadcast across the vehicle's high-speed CANFD or Ethernet networks, making the BMS a master coordinator. It constantly communicates with the motor controller, thermal system, and dashboard. If cells drop to critical thresholds, the BMS triggers power derating, often called turtle mode, to protect the hardware. Conversely, if navigation detects a fast charging station ahead, the BMS coordinates with the cooling loops to precondition the cells, preparing them for high power input before the vehicle even pulls up to the charger. While the basic chemistry of lithium-ion cells is universal, electric vehicle manufacturers apply vastly different engineering philosophies to manage them. For instance, Tesla relies on a distributed, software-heavy architecture designed for frequent over-the-air updates that alter charging profiles on the fly. In contrast, German premium brands like BMW and Mercedes-Benz deploy hybrid, highly redundant systems engineered to satisfy stringent European safety standards. Hyundai's eGMP platform optimizes its management system for ultra-fast charging at 800 volts, while BYD uses a simplified, centralized setup tailored for its thermally stable lithium iron phosphate chemistry. This variation extends to major cell suppliers, with CATL delivering integrated modular platforms to global brands and Northvolt developing specialized high-voltage architectures. These contrasting strategies demonstrate that a traction battery's real-world range, thermal efficiency, and overall lifespan are no longer determined by chemistry alone. Today, the proprietary software driving the system is just as vital as the physical cells. This proprietary software is moving past the physical boundaries of the vehicle. Next-generation systems link onboard hardware to cloud networks, creating virtual digital twins of the battery pack. By mirroring real-time telemetry, machine learning algorithms in the cloud predict cell degradation and identify minor defects long before they cause a physical failure. This cloud integration enables predictive maintenance, warning drivers of potential issues before they manifest on the dashboard. Improved state of health estimation replaces basic voltage lookups with accurate chemical simulations. This data drives adaptive charging strategies, where the system continually refines charging profiles to match the actual physical state of the cells. By transitioning from a static background controller to an evolving AI-assisted software platform, the management system can continuously optimize performance, extending the lifetime of the most expensive component in the vehicle. As global electric vehicle adoption accelerates, the battery management system, or BMS, is no longer just a safeguard, and it is the ultimate arbiter of battery longevity. Next, we will explore how this silent guardian battles a critical threat, lithium plating. Subscribe to join us.